Please do.
Okay, so thanks to my friend Victoria for the introduction. So this is me, and I work with these three people on this specific project. This is my PhD student, Nasser, and these two colleagues are from Loughborough University, and this project was founded by EPSRC, one of the most important sponsors we have in the UK. And actually, I'm starting with a kind of consideration. I was very excited when I got to this project. I started working on 3D printed materials 10 years ago, and now 10 years later, I'm a little bit disappointed because in the end, we are dealing with materials with defects and a problem with the surface. So nothing really new and exciting. So in a way, for me, that has always been the big disappointment when it comes to 3D printed materials. But at the same time, it's unbelievable what we can do in terms of technology. It's where really the nice part of the story is. Okay, when it comes to concrete and 3D printed concrete is seen as one of the future revolutions we are going to have in terms of building new big buildings, which is a kind of true, because in the end you can 3D print concrete, but concrete is concrete, so you need to cure it, plus you need to reinforce it. So as I was saying, this is a big project, and we have two different parts. The first one was studying the mechanical and cracking behavior of 3D printed concrete as such, as a material. So this is what I'm going to do today, materials science. And the other side is going to real applications, so considering also the reinforcement, which is not covered in this presentation today. And actually what we want to do is, again, we want to find a way to model the effect of the defects we have inside a 3D printed material. And what we are going to do is to use the so-called theory of critical distances. So basically we are going to introduce a length scale parameter into our modeling. Okay, so let's go back to the fundamentals. So we have linear elastic fracture mechanics. We know that around the crack we can describe the distribution of the stress using Irwin's equations, and we know that everything is proportional to the stress intensity factor. This is the engineering definition we usually use for the stress intensity factor. I have a pointer here for the stress intensity factor, and this is the remote stress, alpha is the shape factor, and this is the semi-crack length. We can easily rearrange this definition, and we can introduce also an equivalent length of the crack by simply bringing the shape factor into this term. Why is that relevant for what we are going to do? Because basically this is a way to bring any fracture mechanics problem back to the problem of a infinite plate containing a crack loaded in tension. This is the reason why we like to approach the problem here this way. So this is nothing new, this is what we know, and how can we use this body of knowledge to model the presence of manufacturing defects inside of 3D printed concrete? Actually, we need to take a further step to do that. We know that a material fails when the plane fracture or the fracture toughness, the K1 becomes equal to the fracture toughness. So if we play with the usual equations, we can say that a component, and in our case a piece of concrete containing a defect having a certain equivalent length, fails when the nominal stress becomes equal to sigma f, which is the value of the nominal stress, turning K1 or making K1 equal to Kc. So we all know that, and if we use this failure stress together with the equivalent length of the crack, we can plot the strength in a graph like this one. And actually the red line is the line we would get by using this classic formula based on fracture mechanics. So according to this formula, as the defect, the size of the defect or the equivalent length of the defects decreases, the strength increases. And in theory, we would keep going and going and going, because this is a log-log representation. We know that in reality this is not possible, because at a certain point the strength, the nominal strength, would become equal to the material UTS, and we know that the strength of the material cannot be stronger than its UTS. So clearly we have a gradual transition from continuum mechanics to fraction mechanics. And the transition occurs around a critical length, which is what we call the critical distance, and this is the definition of the critical distance. It depends on the fracture toughness as well as on the material UTS. Clearly, based on this schematization, we have two branches, but as we know, as the Latins used to say, natura non facit saltus, that is, nature that never jumps. So we expect a gradual transition from the continuum mechanics region to the linear elastic fracture mechanics covered region. So these little points there. How do we model then this transition? Well, we can then use the theory of critical distance. The theory of critical distance is nothing but a body of knowledge that has been developed over probably longer than a century actually, and giving to this theory many different names. So we have two fundamental ingredients. The first ingredient is an effective stress, and the second ingredient is a material strength. So the effective stress can be defined in many different ways. For instance, according to the point method, we get the effective stress at a certain distance from the notch tip, where this distance is L divided by 2. Remember L as defined in the previous graph. Or we can average the stress over a line where the length of the integration domain is equal to 2 times L. Or finally, we can average the stress over a semicircular area having radius equal to L, and that results in the effective stress calculated according to the area method. So, different versions of the same idea, where the common feature is this critical length L. But actually, we rewrote our problem to bring everything back to the case of a crack in an infinite plane loaded in tension. Why is that? Because if you go back to Westergaard's solution published in 1939, and you have basically a crack in an infinite plate loaded in tension, you have a nice closed form solution which gives you the distribution of the stress, which is singular, on the x-axis, that is along the crack bisector. So you can then use the TCD, the pre-point method, together with this stress distribution, and you can have a nice formula which gives you the failure stress based on the combined use of of Westergaard's solution and the point method. And this nice simple formula was derived by my friend and colleague David Taylor back at the end of the 90s. But you can keep plain, and you can use again Westergaard's solution, and you can average the stress distribution over a line having length equal to 2L, and again you obtain a nice formula giving to you an explicit solution for the effective stress calculated according to the line method. So you play a little bit, and this is the value of the stress resulting in the failure of your component when you apply the line method. All good? So let's have a look at what these formulas do. Basically, they link the plane material behavior with the behavior described by linear elastic fracture mechanics. Here is the case of an infinite plate containing a central crack loaded in tension, but if we play the trick of using the equivalent crack length, that is, we bring into play the shape factor, we can extend this schematization to any possible configuration, and the shape of the course is always the same. So now all the ingredients we need are there. So the point was, can we extend, or the question was, can we extend this theory to 3D printed concrete? Well, we went back to the lab, we manufactured our specimens. I mean, you probably, so far we have mainly talked about metals, but 3D printing concrete means simply extruding a sausage of concrete, and you control the extrusion process and you create the various layers. So it's sausage by sausage, if you like, and you need to prepare a very special mix because you want to have a very fine gravel, otherwise you wouldn't be able to extrude the sausage. you needed to use a suitable super plasticizer, plus you needed to use a proper retarder, so you give to the process plenty of time to settle down after extrusion, and you needed to control the whole process in a quite accurate way using a specific rod, and this is what we did. Plus we changed the print speed and also the volume of concrete that was extruded throughout the process, and after doing that, all the specimens were cured, covered for 24 hours and cured for 28 days. So why did we change these parameters, the printing speed basically? Because if you control the process, you can get a very nice uniform material, as here. It's like a cast concrete. But if you start messing around with your 3D printing technology, you can end up having, all these manufacturing defects. Okay? So we intentionally created a lot of defects, different levels of defects, so that we could explore the accuracy of our theory. Plus, there is another issue, and we will see the issue in a second. So we started considering plain specimens. After that, we considered some specimens where we machined some crack-like notches to simulate real cracks. But also, we observed that in real concrete, since we extrude sausages, we have the same problem as the one we have with metals, surface finishing. So again, this is another issue. And finally, all these defects which can appear during the manufacturing process. So while when we were manufacturing, the conventional or a crack-like notch, it was easy for us to define the crack length. We also decided to define a crack length to model the superficial roughness. So basically the idea was we treated these little valleys as local small cracks. And also when we had this series of defects, we defined an equivalent crack length, assuming that there was no cohesion between adjacent sausages of material below a certain level, and it was very easy to observe the level where you had this manufacturing issue, because intentionally we were creating those bad specimens. And this is the final result. So what we did, we could then, having those definitions, we could apply the usual procedure we use to calculate the shape factor for the various geometries. So we had the shape factor for the various geometries, considering the equivalent cracks. And we used that shape factor together with the definition for the crack depth I showed you in the previous slide, to build up this kind of representation. This is the nominal failure stress, and this is the equivalent length of the defect. And as you can see here, both the point method and the line method can model in a very accurate way the transition from the long crack regime, considering what is a long crack regime for a 3D printed concrete, back to the short crack or the continuum mechanics regime. So we have now a tool which allows us to completely model in full the mechanical / cracking behavior of 3D printed concrete. So we have what we need now to be able to bring into play also the reinforcement, which is, as I was saying, the second step of the project. So, coming to my conclusions, we can say that also with a 3D printed concrete, if you want to use linear elastic fracture mechanics, you need to have an equivalent crack length which is larger than 10L, so which is a quite big crack for a piece of concrete. But if not, you need to move to the TCD, because you need to move that gradual transition. And with the TCD, you can model the surface roughness in a very accurate way, which is very good, because in the end you don't want to over-machine your concrete parts. You want to use them as they are, as much as possible. You can model the presence of cracks and defects. The cracks could be due to, or the defects could be due to the manufacturing process, or also when, due to other problems, for instance, problems you might have during curing. And the good thing is that this simple technique, using standard ingredients, if you like, can be used, can be applied by directly post-processing conventional standard linear elastic FE models. Thank you very much for your attention.
Any question? Please.
Thank you.
Hello, hi, stop.
Just back 2 slides.
Yeah. Here.
One more.
One more. Here.
When you define these equivalent crack lengths, okay, it's clear on at point B, the artificial crack.
Yeah, it was.
Then you have equivalent cracks for the surface roughness and the for manufacturing defects.
Yeah.
Which is more important? Do you have an idea about the influence of each one of them on the final result? And how did you define the equivalent crack for surface roughness?
Okay, the surface roughness is average peak and valley. Like you measure roughness of real components, you scale it up because you know the roughness is way, you don't need to have an accurate tool to measure it. But this roughness, which is the conventional one you get, for instance, we were extruding sausages of concrete having a diameter of 6 millimeters. And this roughness here, just to tell you, sorry, you are basically here. Okay, it's a log-log schematization, but compared to the plain material behavior, you have a reduction which can be up to 20–30% in terms of strength. So it plays a very important role in that. And I can tell you, we were 3D printing benches at the very beginning, and those benches were cracking, and we were like, it's impossible. And actually, we got to the point, because when we were sitting on the benches, we were pushing them, and the roughness was in the back, opening and cracking. Having said that, silly things we were doing in the lab. Okay, when it comes to this definition here, clearly you need to observe your material. You might say,
it's somehow empirical.
I mean, because here you can clearly see where you have the last bad defect, and you can clearly see that, you know, you can clearly define your equivalent crack. I understand that when you have a real component, it can be more difficult, but at least you have a tool which allows you to somehow judge the level of damage you are or your defect is causing in your material. And also, I mean, clearly one of the criticisms here might be that, okay, well done, Luca, but here you are clearly modeling a crack in a bidimensional plate, and you say, yes, I agree, but the geometry is so complex. And the other question is, what about the thickness? Clearly the distribution through the thickness is different, and in a way you are simplifying the process, because 3D printed concrete is very rough in terms of geometry. So yeah, but also you cannot be very accurate, so really you need to simplify the process. And clearly this is a big simplification, because we were calculating the shape factors assuming how can I say, a numerical crack in a high-dimensional body. Clearly it's a simplification.
Thank you.
Thank you. Very quick question, very interesting. I was very intrigued about how you put the weight factor into the square root to create an equivalent crack. But we know these weight factors are often empirical, and some have analytical solution, but some have empiricism. So including that within a equivalent crack length, shouldn't it create more error in predicting things? Just a thought.
It depends. It depends. I mean, yes, you know, but how can you extend fracture mechanics to other components? I mean, if reality were based on infinite plates with cracks, we would be at home right now doing something else. So yeah, it's an issue there. It's an issue there, but I don't. Sorry, it's an assumption. I mean, and to be honest with you, just to be fair, I don't want to claim that I invented that. If you go through the Japanese literature that was published back in the 60s, 70s, 80s, even Professor Murakami himself, they introduced this idea of moving the shape factor.
All the ideas come back again.
They come back as always. We are inventing the wheels.
It's only that we have no so
It's very
much time.
interesting. It's very interesting.
We are inventing the wheel so we can pay the bills and eat twice a day.
We have to do it.
We are academics, isn't it?